See, calculation of degree of freedom and total energy of gas molecules, right? See, degree of freedom for gas molecules. So suppose that a molecule has number of atoms. A molecule may be monoatomic, diatomic, triatomic, polyatomic, right? So let the molecule let the molecule have number of atoms is equal to n, right? For example, if you take helium, so for helium n is equal to 1 monoatomic. For hydrogen n is equal to 2. For ozone n is equal to 3. For CH4 n is equal to 5, right? So n are the number of atoms present in the molecule, so the total degree of freedom, right? Total degree of freedom, right? So total degree of freedom is equal to total degree of freedom is equal to 3n, right? Means total, translational, rotational plus vibrational. Total means, here total means translational plus rotational plus vibrational. Total means this. So total translational, rotational and vibrational degree of freedom is equal to 3n, right? Now, number 1, first, translational degree of freedom, degree of freedom is equal to 3. Always for all kinds of molecule. Means whether it is monoatomic, diatomic, triatomic, polyatomic, whatsoever the molecule, the translational degree of freedom is always equal to 3, right? Second is rotational degree of freedom. Rotational degree of freedom this depends on the geometry of molecule. Depends on geometry. So already all of you have gone through the chemical bonding. So all of you are knowing what kinds of geometry. So here only two kinds of geometry are considered to be for this rotational degree of freedom. One is linear. For linear molecules, the rotational degree of freedom is equal to right? Means every linear molecule definitely that will lie on the some axis, either x or y or z. So if a linear molecule lies on this suppose that on x-axis, so now this about this axis this cannot be rotated, so left two axes are left about which it can rotate. So the rotational degree of freedom is 2. Translational degree of freedom for every molecule, you know, translational motion, whole molecule shift in the direction of the force. So all three axes are free for every kind of molecule to translate. But rotational degree of freedom for linear molecules, it is only two axes are free to rotate. And for non-linear molecule, molecule rotational degree of freedom is equal to 3. All three axes are free to move. For example, if you see, suppose that if you take methane, which is a tetrahedra molecule like this. So translational degree of freedom is equal to 3. Any number of molecules may be there. Rotational degree of freedom, so this is linear or non-linear, this is non-linear, so this is non-linear molecule, so rotational degree of freedom is equal to 3, right? So this is how to calculate this rotational degree of freedom. Now see, the third one is vibrational degree of freedom. So as all of you are knowing, vibrational motion is the internal motion degree of freedom. You know, vibrational motion is the internal motion of atoms within molecule. This is not the external motion. So through and fro motion, like suppose that if you take a hydrogen molecule, so all of you are knowing that the bonds are like a spring, and both the hydrogen are always in the through and fro motion, means like this: compress, relax. This is called vibrational motion. So although we have different modes of vibration, rocking, scissoring, bending, stretching, all these are the different modes of vibration, but here we are not going into that detail. So this is vibrational motion. So vibrational degree of freedom, no need to do anything. You have total degree of freedom 3n, you have translational, you have rotational. So what you can do, you subtract simply rotational plus translational from total and get the vibrational degree of freedom. So vibrational degree of freedom for linear molecules, the total degree of freedom is 3n minus 3 plus 2. 3 translational and 3 is the translational and 2 is the rotational. So your formula becomes 3n minus 5, right? And for non-linear molecules, this is equal to 3n minus 3 plus 3, translational and rotational, right? So this is equal to 3n minus 6, right? So vibrational degree of freedom, this is and if you see rotational and translational, they are fixed. So only the vibrational motion, vibrational degree of freedom has the great scope. And you know, as you increase the number of atoms in the any molecule, there is no increase in translational or rotational degree of freedom. The only vibrational degree of freedom increases. So if you keep on increasing the number of atoms in any molecule, what you will get finally, the giant molecule, and it becomes solid. So this is the reason why in case of solid, the greater contribution is of the vibrational degree of freedom, vibrational energy, not the rotational and rotational and translational, right? So vibrational degree of freedom, this is more contributing in case of liquids, in case of solids than the gas. In gas, translational and rotational are major contributor, right? So for example, if you see for methane molecule, for methane, as we know, the translational degree of freedom, is equal to 3. Rotational degree of freedom is equal to 3, and vibrational degree of freedom is equal to 3 into 4 and 1 5, 3, and this is the total degree of freedom, total minus 3 plus 3, translational plus rotational, right? So this is equal to 15 minus 6 is equal to 9, right? So there are 9 different modes of vibrations possible in case of methane, right? So in this way you can calculate the degree of freedom. Another example, if you take carbon dioxide and sulfur dioxide. See, so first you have to determine the geometry. This is linear, as you know, with the help of bonding. If your bonding is not clear, you cannot do this question. And sulfur dioxide, this is non-linear. Bent structure, non-linear. This is sp hybridized. Linear, this is sp2 hybridized. Sulfur is sp2. Here carbon is sp. So this is linear and this is non-linear. Now the number of atoms 2 and 1 3. So total degree of freedom is equal to 3 into 3 is equal to 9. Here also the total degree of freedom is equal to 9, right? Now translational degree of freedom is equal to 3. Here also translational degree of freedom is equal to 3. This is a linear, so rotational degree of freedom is equal to 2. This is non-linear, so rotational degree of freedom is equal to 3. is equal to 3, right? So vibrational degree of freedom, is equal to 9 minus 5 is equal to 4, and here vibrational degree of freedom is equal to 9 minus 6 is equal to 3. So in this way you can calculate translational, rotational and vibrational degree of freedom for different molecules, right? So see, both the molecules have same number of atoms, total degree of freedom is same, 9 and 9, translational is same, they have difference in rotational and vibrational. So in this way you can calculate the total, translational degree of freedom. Now calculate the one more example. See, calculate the energy. Calculate the total energy of helium gas molecules at temperature T. Right? So first you have to see the gas helium. This is monoatomic. So translational degree of freedom is equal to 3. Rotational, no. Vibrational, no. Right? So translational degree of freedom is equal to 3, and this is equal to the total degree of freedom. Right? So and each degree of freedom is associated with half RT energy. So E total is equal to E translational, because only one motion is possible in case of helium. So this is equal to 3 into 1 by 2 RT per mole, means 3 by 2 RT, as we have proved this formula in gaseous state as well. So for this helium or monoatomic gas, total energy is basically translational energy. Total energy is translational energy. So it is whether they have asked translational kinetic energy or total energy, you can calculate the same. But if in place of helium, suppose that the question is given, find or calculate total energy of hydrogen gas molecules at T Kelvin, right? So hydrogen diatomic linear. So this is the part of chemistry, right? Now simple formula: translational degree of freedom. Translational degree of freedom is equal to 3. So E translational is equal to 3 into 1 by 2 RT. right? Now rotational degree of freedom, is equal to 2. So E rotational is equal to 2 into 1 by 2 RT, right? And vibrational degree of freedom is equal to 3n minus 5, 6 minus 5 is equal to 1, right? 3 to just 6, 6 minus 5 is equal to 1. So E vibrational is equal to 1 into RT. So the total energy E total thermal is equal to 3 by 2 RT plus 2 into 1 by 2 RT plus RT. This is vibrational, this is rotational, and this is translational. So 3 by 2 RT plus RT and RT 2 RT. So this is equal to 7 by 2 RT, right? So this is the E total. Okay. So for diatomic molecule, you can calculate E total in this way. See, depending on the temperature T, you can ignore this. At room temperature, the contribution of this is very low. So you can write here if T is room temperature, right? Then E total, you can write E total is equal to 3 by 2 RT plus RT is equal to 5 by 2 RT, right? In most of the physics books, you will get this energy 5 by 2 RT for diatomic molecules, right? But this is without contribution of vibrational energy. If you include vibrational energy, then this is 7 by 2 RT. So in this way you can calculate. That's why at that time in the gaseous state I have not explained this. Now it is over, that now you are able to calculate energy of any kind of gaseous system separately, translational, rotational and vibrational, and total energy as well. So this is the reason why in gaseous state in many books you will find the incorrect interpretation. In the question, in the numerical, they were asking find the total energy, and finally they are calculating only translational energy. So now you becomes more clear what question but this is not, this will not repeat in this type of mistake will not be there in the IIT-JEE advanced paper. So be ready what they have asked, whether when they have asked total energy, so you have to consider total energy means translational, rotational, both, right? And at room temperature ignore vibrational, but at higher temperature this vibrational also contributes, right? At higher temperature vibrational also contributes, remember my words. So as per the requirement of the question, you have to answer, right? And I have given you all the concepts related to this. So now this concept of internal energy is over. And one more thing, that this is extensive property, internal energy change. This is extensive. This is extensive, right? This is extensive. And if you take molar internal energy change, this per mole, this is change in internal energy. Energy per mole. So this is intensive. Molar property. So this is intensive. And this is a state function. State function means, if you take this in the cyclic process, means if you start from some initial state and return back to that state, so total change is 0. So this is a state function and extensive quantity, and it is defined as E can be written as a function of T, V and N. So this is a very fundamental equation which gives the complete variation in internal energy with the variables. If it is not a state function, then you cannot write this statement, this mathematical expression. So if you want to make the complete change in the internal energy, so do the partial differentiation of this equation. Hopefully all of you are knowing partial differentiation. See, change in internal energy per unit change in temperature, del E by del T at constant V and N. So this is the derivative, you can say, change in internal energy per unit change in temperature, and if you multiply this whole with the total change in internal energy, so you will get, total change in temperature dt. So if you multiply this change in energy per unit change in temperature with the total change in temperature, so you will get the total change in internal energy for that temperature change plus del E by del V at constant T and N dV. This is the change in energy per unit change in volume, and this is the total change in volume. So you will get the total change in internal energy due to the change in volume plus internal energy change with the change in the number of moles as well. So this is T and V and Dn. So this is a very exhaustive expression which explains the total dependency of internal energy on the different variables. Means internal energy can be changed with the temperature, can be changed with the change in volume, can be changed with the number of moles. No need to include the pressure here, because all of you are knowing that to explain any state function for gaseous system, homogeneous gaseous system, only 3 variables are chosen. So this is a definition basically. This is defined in this way. Don't put here question, why sir you are not taking pressure here? Because we are not defining this internal energy in terms of pressure. This is the simple answer, right? So don't be confused that why not pressure is here, why you are not writing in terms of pressure. No need to write the pressure, because at any moment of time, if we want, we can calculate the pressure, right? But since it is defined in this way, so you have to perceive, or you have to follow this way only, right? Now see, if your gas, this is the very general equation number 2 is applicable for any type of system, whether it is a real system or ideal system. Any type of system can be explained with the help of this. Now I am imposing some restrictions. Suppose that the nature of the gas, ideal. Nature of the gas is ideal. If the nature of the gas is ideal, then what will happen? This del E by del V, basically this del E by del V, this is equal to the internal pressure. Internal pressure. This is equal to N square A by V square, right? And this is equal to 0 for ideal gas. Remember, internal pressure, van der Waals equation, energy by volume, unit of energy by unit of volume, we will get the pressure. So this pressure is known as internal pressure basically. So this internal pressure is equal to N square A by V square, and this is 0 for ideal gas. So this term is 0 for ideal gas. Means internal energy is independent of change in volume for ideal gas. Right? And if you want to calculate the change in internal energy for a real gas, in place of this you can put this and integrate and get the change in volume. Second, restriction I am imposing here, that for a closed system, when you are taking a closed system, there is no exchange of mass between system and surrounding, means there is no change in the number of moles. So for closed system, delta N is equal to 0, right? Until or unless there is no cleavage of bonds during any process in the system, right? So dN is equal to 0, so this term is also 0, this term is also 0. So delta E is equal to, you can write del E by del T at constant V and N and dt, right? This is equation 3, okay? And this is valid for a closed system and ideal behavior of gas, right? So this is very fundamental equation which tells about the change in internal energy, for an ideal gas in a closed system. If your system is not closed, there are some change in the number of moles, then you have to include this. And if your behavior of your gas is not ideal, so you have to put N square A by V square in place of this and integrate this and get the change in internal energy. But this is not required for you people, but you just know this is not any difficult point, right? So you can write here that in a closed system for any ideal gas, note for any ideal gas, for ideally behaved gas, internal energy is the function of temperature only in closed system, right? So suppose that the question is given, some example is given that an ideal gas expanding from 10 liters to 20 liters at 300 Kelvin, right? At 300 Kelvin. Find the change in internal energy. 1 mole of an ideal gas, we can write here. 1 mole of an ideal gas is expanding from 10 liters to 20 liters. So see, initial 10 liters, 20 liters, number of moles. So you can formulate this. See, any gas is not specified. So suppose that gas A is the gas. Suppose that initially it is 1 mole and 10 liters and 300 Kelvin. It is changing to same A gas, 1 mole and 20 liters, right? And temperature is 300 Kelvin. So this is change in state, it is shown here. Don't bother about pressure will accordingly change, and don't bother because you have PV is equal to nRT. If you want, you can calculate what is the pressure here and what is the pressure here, but not required. Okay, now see, an ideal gas, right? Ideally we have the gases there, and temperature is constant. See, 300 Kelvin initially, 300 Kelvin initially, 300 Kelvin finally, means delta T is equal to 0. So if delta T is equal to 0 and internal energy depends only on temperature, so you can directly write delta E is equal to 0. So there is no change in the internal energy. See this equation, if you put here dt is equal to 0, your delta E is equal to 0. Means if a gas behavior of which is ideal is expanding or compressing, is under expansion or compression at constant temperature, the change in internal energy is always equal to 0. But if I remove this part from here, ideal, if I remove here, then your answer is not 0. Then I have to give you the value of van der Waals constant so that you can evaluate how much change is taking place in internal energy with change in volume. So be extra careful when you are reading any question. You should be focused that what is the behavior of the gas. Okay, in many cases we are here to deal with ideally behaved gases, but not always in IIT-JEE advanced like exams, right? So this is the change in internal energy and how on what factor is internal energy is depends, right? Now next I am taking here work and heat, and after that I will talk about the thermodynamics first law. Well, see, first we see sign convention, then I will talk about work and heat, and after that thermodynamics first law, right? See, this sign convention, it is basically based on, because every convention has some basis. So if you know the basis, then it is very easy for you to understand this convention, right? Many times there is a confusion in physics versus chemistry, but I don't know what convention, what I mean reference physics people are taking. I am only knowing my subject, that in chemistry, this sign convention is based on energy of system, energy of system. Means for a chemistry people, the main focus is on the system, right? Any factor, listen carefully, any factor which increases the energy of the system, taken positive, considered positive, and any factor which decreases the energy of the system is taken negative. This is the, I mean, basis of sign convention. So first I am generalizing this. Any factor increases the energy of the system, energy of the system, whatsoever that factor is taken positive. That factor taken positive. Means if work, suppose that if you, I mean your system involves some work, and due to that work, if energy of the system increases, then the work is taken positive. And second, any factor, any factor decreases the energy of the system, decreases the energy of the system, energy of the system, then that factor taken negative, taken negative, right? Now see, suppose that you have a system, and your system have some I mean gas. Suppose that here this is T gas, and here T external. Suppose that, and this wall of the material is diathermic. The material wall is diathermic. Diathermic means which allow the flow of heat, right? Then what will happen if T gas is equal to T external? Means thermal equilibrium, system and surrounding are in thermal equilibrium, and no net heat change. no net heat change between system and surrounding, right? Means there is no heat change, net heat change between system and surrounding. Now see the second case. This is the first case. In the second case, when T system is greater than T external, in this situation, some heat is transferred from system to surrounding. Some heat. Why this heat is transferred? Net heat is transferred from system to surrounding. There is some heat may flow from surrounding to system, but the resultant heat will transfer from system to surrounding to maintain the thermal equilibrium, right? So since heat is a kind of energy, so heat energy transferred from system to surrounding, so the energy of system, so this time energy of system system decreases. Energy of system decreases. So if energy of system decreases, due to which factor? Due to the transfer of heat, then due to transfer of heat, thus heat means Q is taken negative, because this heat is decreasing the energy of the system. Hopefully all of you are getting this point. So whenever T system is greater than T surrounding or T external, there is a net heat transfer from system to surrounding, result of which the energy of the system decreases, and due to this energy of system decrease, that factor is considered negative, which decreases the energy of the system. So heat transfer decreases the energy of the system, so you have to take heat as a negative, right? Now third case, if T system is less than T external, it is less than T external if T external, energy of system increases. This is due to the transfer of heat. This is due to the transfer of heat from system to surrounding. And this time, this is due to the transfer of heat. This is due to the transfer of heat from surrounding to system. So this time heat is taken negative. Thus heat Q is taken positive, not negative, taken positive. Clear? So this is the concept of the sign convention, that when you are taking heat as a positive, when you are taking heat as a negative, right? So heat transfer, basically it is the result of temperature difference between system and surrounding. One more way to change the energy of the system, that is work, right? So second case, suppose that we have taken a system like this, and in this system we have taken a massless and frictionless piston here. This is a massless frictionless piston, and here we have taken some gas. This time this P gas, pressure of the gas is P gas, and here P external. So first case, in this first situation I am taking that P gas is equal to the P external. So the system and surrounding are in mechanical equilibrium. Mechanical equilibrium, right? Means there is no change in the volume. There is no change in the volume in this situation. Means there is no work. So you can say no PV work, pressure volume work. Because the cause of pressure volume work is what? The pressure difference between system and surrounding. Okay. Second case, when P gas is more than P external, so in this situation, what will happen? Piston shifted outside because this gas will work on the external pressure, right? So if gas will work, means work is done by the gas. So P gas is more than P external, the work is done by the gas, is done by the gas. And if gas is doing work, means the energy of the system decreases, the result of which energy of system decreases, and thus work WPV, basically I am talking about PV work here, pressure volume work, this is what? Negative, because this will decrease. This in this situation energy of the system decreases, right? Clear? Good. Now third case, see, when P gas is less than P external, all of you are knowing that pressure is a type of potential which determines the flow of mass. So this time the work is done by the surrounding on the gas. So the work is done on the gas, result of which energy of system increases, and therefore thus work, means PV work, it is taken positive. So any factor which increases the energy of the system, that is taken positive, and any factor which decreases the energy of the system is taken negative. This is the sign convention in thermodynamics. So basically sign indicates that energy is flowing from where to where. Negative sign means energy is flowing from the system to surrounding. right? So basically this sign gives the direction, direction of flow of energy, flow of energy, right? Negative means system to surrounding, and positive means surrounding to system, surrounding to system, right? So whenever you found any sign with any symbol, suppose that I have written here WPV, WPV is equal to minus 20 joule. So how to interpret this? You can interpret that 20 kilojoule energy is involved in this PV work, but this energy is released from system to surrounding. See, directional flow of system to surrounding means this energy removed from system to surrounding, right? So suppose that if you are given a system and this has some energy, suppose that E, and it is given that from this for this system W is minus 20 joule, so minus 20 joule. So what is the final energy of your system? So the final energy of our system is E minus 20. And suppose that the surrounding energy is E dash, so this is the E minus 20 is the energy of the system, energy of system. And what is the energy of surrounding? So energy of surrounding is equal to E dash plus 20, E dash plus 20. So basically this is the convention. If anywhere it is written W is equal to minus 20 joule, means 20 joule of energy transferred from system to surrounding in the form of work, in the form of work, right? So energy of the system, this is finally, and this is the energy of the surrounding finally. So if you add these two, figures, E minus 20 plus E plus 20, E dash plus 20, so you will always get energy is conserved. Energy is conserved. So this is the basically thermodynamics first law. So the thermodynamics first law states about the law of conservation of energy, but one condition is there: your system should be isolated. So if you add system plus surrounding, then you will get the whole universe, and universe is the best isolated system, right? So in an isolated system, the energy of the system plus energy of the surrounding, this is conserve. And this is basically first law of thermodynamics. So slowly we are heading towards thermodynamics first law. So this is the sign convention and interpretation of different parameters. Suppose that if at any point of time it is written plus 10 joule, so Q is equal to plus 10 joule means energy of the system is increases by 10 joules as a result of transfer of heat from surrounding to system to maintain the thermal equilibrium, right? So it has many meaning here that system accepts or system absorbs 10 joule energy from surrounding. from surrounding, right? Second interpretation you can write that energy of system increases by 10 joule. Energy of system increases by 10 joule, right? And you can say this transfer of this energy, heat energy, is due to the temperature difference. Means there is a temperature difference between system and surrounding, right? So initially there was a temperature difference between system and surroundings, right? So these are the different interpretations you can interpret on the basis of this. And positive sign means energy is flowing from surrounding to system, right? So in this way you can interpret all these things.